Hello learners, welcome to Constant Learners. In the previous video, we've discussed attribute closure and we looked at some simple examples of how to select superkeys and candidate keys in a relation. In this video, we are going to solve three different examples to be able to find all the candidate keys in a relation. This is a very important question from a competitive examination point of view, especially GATE and UGC NET. You get these types of questions wherein you have to find the candidate keys from the relation, right? So I hope that you understand what are superkeys, what are candidate keys, and what is attribute closure. All of these three concepts are very important for us to be able to understand this video properly. Also, this concept is very important to be able to understand the normal forms that we're going to discuss in the further videos. Also, before we begin, if you haven't already subscribed, please subscribe to my channel, hit the bell notification so that you stay updated every time I upload a new video. And if you like this video, don't forget to give it a thumbs up. Let's begin. So this is our first example wherein we have the relation PQRST. That means the attributes are PQRST and the functional dependencies given are P determines Q, QR determines S determines T, and T determines P. Right? Now let's say we have to find all the candidate keys in this relation. Now anytime if you get this type of question, first thing that you should see is the right hand side of the functional dependencies, right? Let's check which attributes are present on the right hand side of the functional dependencies. Here we have Q, S, T, P, right? So we have Q, S, T, P. The only attribute that is not present on the right hand side of the functional dependency is R. Now, all of these attributes that are present on the right hand side of the functional dependencies will be somehow determinable. That means we can somehow determine these attributes, right? These attributes are determinable. We only have to worry about the attribute that is not present on the right hand side of the functional dependency. Now, what do we need to worry about that? See, an attribute can determine itself as per the reflexive property. So, R will be able to determine itself, right? So, the first thing that we understood from here is that R will always be present in every superkey and candidate key because it cannot be determined by any other attribute, right? So, R will always be present in every superkey as well as the candidate key. So, we are going to start from here. For this problem, if you have these kinds of problems, these are very quick to solve because we directly have to start with the attribute R, right? With attribute R, we are going to combine the first attribute that is P and find the attribute closure of this, right? Let's check. P will determine itself and P can determine Q. So we are getting PQ here. Then R will determine itself, right? Now, if P determines Q and QR determines S, right? Then we can write that PR determines S as per the pseudo transitivity rule. It is important that we know all the Armstrong's axioms, okay? Because we are going to use only the Armstrong's axioms to solve these problems. So we need to know all of these Armstrong's axioms, right? That video is also uploaded on the channel. I'll link that above as well as in the description below, right? So now, if P determines Q and QR determines S, then as per the pseudo transitivity rule, PR can determine S. So now this PR can also determine S, right? Now, if PR can determine S and S can determine T, then we can write that PR can determine T, right? So we are also getting T here. We've got all the attributes on the right hand side. When we get all the attributes on the right hand side, then PR will be the super key. So this here, this PR, this combination is our super key. But will this be a candidate key? That we will have to check. Candidate key is minimal super key. Minimal super key means what? Any proper subset of super key should not be a super key. The proper subset of PR is P and R. So the attribute closure of P and R, these should not be the super keys. Let's check. P can determine itself and P can determine Q, right? P cannot determine any other attributes because to determine S we need R and we don't have R. So this is not a super key. Then R. R can only determine itself. There is no other attribute that R can determine. So this is also not the super key, right? That means PR will become the candidate key. Simple. We started with the attribute that is not present on the right hand side, combined it with one other attribute, and we got our first candidate key. Now, what are the prime attributes of this candidate key? Prime attributes are the attributes that are used to make this candidate key, right? So the prime attributes here are P and right? Now, R is not determinable by any other attributes, but P can be determined by some other attribute. Yes, T can determine P. Now, we are going to replace this P with T and check if that will be a super key and candidate key or not, right? So, the next combination that we are going to check is T, R, right? T can determine itself and T can determine P, alright? R can determine itself, right? Now, if T can determine P and P can determine Q, then we can write that T can determine Q as per the transitivity rule, right? So here T can also determine Q. Now if T can determine Q and QR can determine S, then we can replace this Q by T and write that TR can determine S as per the pseudo transitivity rule, right? So here we're also getting S. So we've got P, Q, R, S, T. We're getting all the attributes here. That means this will definitely become a super key. But will this be a candidate key? We will have to check. See, R itself is not a super key. Here we've already checked that R is not a super key. So we will only have to check T. Let's check the attribute closure of T. See, in the beginning only we have declared that every super key and candidate key will have the attribute R. So checking this is entirely useless, but we are just checking for our understanding, right? So T can determine itself and T can determine P. If T can determine P and P can determine Q, then T can also determine Q. But to determine S, we need R, right? And R is not present here. So this is not a super key. That means TR is also a candidate key, right? So the prime attributes are T and R. Now similarly, let's check which attribute determines T. So S is determining T. So here we can replace T with S and check if SR is a super key and candidate key or not. So S will determine itself and S determines T. Now if S determines T and T determines P, that means S will also determine P as per the transitivity rule. If S determines P and P determines Q, then S will also determine Q, right? And R will determine itself. Again, we are getting P, Q, R, S, T. We are getting all the attributes. Hence, this will be a super key. But will this be a candidate key? Yes, of course it will, because R is not a super key in itself and S cannot determine all the attributes. S can only determine T, P and Q. But can S determine R? No. R is not determinable by any other attributes, right? So then this cannot be a super key and therefore the combination SR will be a candidate key. Now here the prime attributes are S and R. Now again S is determinable by Q and R. So we can replace S by Q and check if QR is a super key or not. Very quickly, Q can determine itself and the combination QR can determine S, R can determine itself. Then if QR can determine S and S can determine T, then QR can also determine T. So here we're also getting T. If QR can determine T and T can determine P, then QR can also determine P. So again, we're getting all the attributes and this will also be a super key. And will this be a candidate key? Yes, it will be a candidate key because without R, Q alone cannot determine all the attributes, right? So it is not going to be a super key. These are all the candidate keys that we can get in this relation, right? Now the next example is a little different than this one, right? Alright, here we have the relation with attributes M, N, O, P, Q, R, right? And functional dependencies are also given. First thing I told you is we need to check the right hand side of the functional dependencies. Here we are getting O, P, Q. So we are getting O, P, Q, R, N, M. R, N, M. Now here, all of these attributes are present on the right hand side of the functional dependency. In this example, R was not present in the functional dependency and thus we were starting with R, right? But here all the attributes are present in the right hand side of the functional dependency. So now we are going to take the attribute closure of all of the attributes. We will start with all the attributes. Now in this problem, we are going to go step by step and take a little lengthier route, alright? But in the next example, we are going to try and find shortcuts to be able to solve this problem, right? Now, every attribute will determine itself, M will determine itself, N will determine itself, O, P, Q, R. So we are getting all the attributes here. Hence, this is definitely a super key. Will this be a candidate key? No, because at least some of the proper subsets of this key is going to be a super key. Let's check. Now here we have MN, right? Let's start with MN. MN will determine itself, right? And MN will also determine O, right? So now we don't need O here because O has already been determined, right? Then we need P because O determines P and Q. There's no other attribute that can determine P. So we will write P here and P will determine itself. But we will need Q here because there's no other way to determine Q. So Q will determine itself, right? Then Q will also determine R. So we don't need to write R on the left hand side because Q is already present here on the left hand side and it can determine R. It's given here. This functional dependency says Q determines R, right? So this M and PQ will also be a super key. But will this be a candidate key? Let's check. See, if Mn is determining O and O is determining PQ, then as per the transitivity rule, can we say that Mn determines PQ? Yes, Mn determines O and O determines PQ. That means Mn determines PQ. Then we can decompose these, right? As per the decomposition property, we can write this as Mn determines P and Mn determines Q, right? We can write it like this. We can only decompose the right hand side, okay? We can only decompose this side. We cannot decompose the left side, right? Now, if Mn is determining Q and Q is determining R, then we can write that Mn determines R, right? So now again, let's omit PQ from here and start with only Mn, right? Let's check the attribute closure of Mn. Mn will determine itself. Mn also determines O, right? Then Mn also determines P and Q. So here we will also get P and Q. And Mn is also determining R, right? So this is also a super key. Now for this to be a candidate key, the proper subsets should not be a super key. That means M and N alone should not be a super key. Let's check. See, M can determine itself, but M cannot determine any other attribute. We need a combination of Mn to determine O. N can also not determine any other attribute. So both of these are not super keys. And thus we can say that Mn is a candidate key. Now the prime attributes here are M and N, right? Now M is determinable by O, right? So we can replace M by O. Let's check On. Let's check if On is a super key or not. O can determine itself and O can determine P and Q, right? So we can write this as O determines P. We can split this, right? We can decompose these two as O determines P and O determines Q, right? Now if Q determines R, then we can write that O can determine R, right? N can determine itself, right? And O can also determine M. So we are getting M, N, O, P, Q, R. We are getting all the attributes here and this will be a super key. But is this a candidate key? Now see, this N is not a super key, right? So we only need to check O here. The proper subset, that is O, should not be a super key. O determines itself. O determines P and Q. O also determines R because O determines Q and Q determines R. So O also determines R. Then O determines P and P determines N. So we can say that O determines N, transitivity property, and O is also determining N, right? So now O is able to determine all the attributes and hence O is a super key. Thus, in this case, On cannot be a candidate key, but O alone will be a candidate key, right? So the prime attribute that we're getting here is O. Now O is determinable by Mn, but Mn is also a candidate key. Now we replaced M by O and we got this. Can we replace N by P? Because N is determinable by P. So let's replace N by P in this combination and check. Let's take the attribute closure of M and P, right? M can only determine itself. M cannot determine anything else, right? M alone cannot determine O. We need N to determine O. But P can determine itself and P can determine N, right? But there's nothing else that MP together can determine, right? Mn is determining O and P is determining N. But this combination cannot give us any other functional dependencies. Hence, this is not a super key. Now we cannot have any other combinations here. So we've received two candidate keys. One is MN and the other one is O. Now let's head to the next example. In this next example, we are going to try to be a little quicker, right? First, we are going to check all the functional dependencies here, and then we will try and solve the problem. So the functional dependency is given here. AB determines C, C determines D. Now, as per the transitivity rule, here we can write that AB determines D, right? Now, if AB determines D and D determines EF, now this D determines EF as per the decomposition property, we can write that D determines E and D determines F, right? As per the decomposition property, correct? Then, if AB determines D, then we can write that AB determines E and AB determines F. We can start with AB here. Let's find the attribute closure of AB. AB can determine itself. AB can determine C. AB can determine D, E, F. E, F. That means AB can determine all the attributes, hence it is the super key. But will this be a candidate key? Only if the proper subsets are not the super keys, right? If proper subsets are super keys, then AB will not be a candidate key. But A can only determine itself. C, A cannot determine anything else. The combination of AB can determine C. And B can also only determine itself. So this is also not a super key. This is also not a super key. Hence, AB will be a candidate key. So the prime attributes here are A and B. Now, A is determinable by F. So we are going to try and replace A with F first, right? Let's check if FB is a super key or not. F can determine itself, B can determine itself. Then F can determine A. Now, if F can determine A and AB can determine C, then we can replace this A by F, right? As per the pseudo transitivity property, right? And we can write here FB determines C. So we got C here. If FB can determine C and C can determine D, then we can write that FB can determine D, right? If FB can determine D, then FB will also be able to determine E. All of this with the help of transitivity property. So this is a super key. But will this be a candidate key? See, B is not a super key. We've already checked here. Let's check if F is a super key or not. F can determine itself. F can determine A, right? Can F determine anything else? No, because to determine C, we need B, and there's nothing else that F can determine. So this is not a super key. Hence, FB is a candidate key, right? So prime attributes are F and B. Now, F is determinable by D and B is also determinable by D, right? So what should we do? We can either replace F by D or we can replace B by D. Let's try with DB, attribute closure of DB. So we are replacing F by D, right? D can determine itself. D can determine E and F, right? If D can determine F and F can determine A, that means D can also determine A as per transitivity property. D can determine A, and D can determine B. It is already given, right? Now, as per the union property, we can write that D determines both A, B, right? In the union property, if left hand sides are same, we can combine the right hand sides. Now, if D is determining AB and AB is determining C, we can write that D is determining C. So, you've got all the attributes A, B, C, D, E, F. So, this is a super key. But will this be a candidate key? See, B is not a super key, but we will have to check the attribute closure of D. See here, D can determine A, D can determine B. So we are getting both A, B. Then since D is determining AB and AB is determining C, D can also determine C. D can determine itself, yes. Then D can also determine E and F. So we are getting all the attributes here. Hence, this is also a super key. So DB cannot be a candidate key, but D alone will be a candidate key. So the prime attribute is D. Now D is determinable by C. So we'll check if C is a super key or not. So C can determine itself. C can determine D. D can determine E and F, and C can determine D. So we can write that C can determine both E and F as per the transitivity property. If C can determine F and F can determine A, then C can also determine A. If C can determine D and D can determine B, then C can also determine B. So we are getting all the attributes here. So this is also a candidate key. This is a super key. C is a super key. It cannot have any other proper subset. So this will also be a candidate key. So we've got C here. Now A is determinable by F. So we've checked with F. B is determinable by D. We've checked with D. D is determinable by C. Alright. So we've replaced all the attributes and we've checked and we've received total 4 candidate keys. And the total prime attributes are A, B, C, D and F. And the non-prime attribute, now the only attribute that is left which has not been used to form any candidate key is E. So E will be the non-prime attribute. This is very important because the next video is going to be partial dependency and we need to understand what are prime attributes and non-prime attributes to be able to understand partial dependency. Right? These problems are very simple. You just need to be thorough with your Armstrong's actions and you must know how to find the attribute closure and select the super keys and candidate keys. If you know this, these problems are going to be a piece of cake and we cannot lose marks on these problems, right? These are very simple problems. So we cannot afford to lose marks on these problems. We just need to practice and with practice, we'll be able to solve these problems very easily. Alright? If you understood this video, if the problems were helpful, don't forget to give it a thumbs up, subscribe to the channel and thank you so much for watching.